And now when we get into the more technical side of the discussion, I'm going to bring up Tatjana, who works with us at Autodesk, and she's going to spend some time telling us more about these emerging trends in this area. So Tatjana, please join us up here on stage. Thank you.
Hi, thanks. Thank you. Wowzers. It's only 1 year since the last AU, and it feels like we live in a completely new place. By the way, the slides have not changed? Yep. The future does not seem to be what it used to be last year. So we start to talk about additive manufacturing, AR, VR, robotics, machine learning, artificial intelligence, and to pretend that, that everything is just normal. Well, it's not. Things are happening so fast that we need to react. Today, I would like to talk to you about these trends. What are they? Why should you care? And what are we at Autodesk doing about it? And as you will see, almost all of them on their own have an impact on the future of making things. But all of them together are going to converge into something profoundly new. We're on the verge of a revolution. It's technological, it's social, and it's cultural, and it's called infinite computing. Infinite computing happens as a convergence of 3 trends. Number 1, the exponential increase of computational power. Number 2, democratized access to that power. And number 3, precipitous fall of the price, of the cost of that power. Now combine that with the power of the cloud, and for the first time, we have an ability to apply tens, hundreds, 10,000s of computers at the same time to solve the ever-emerging problems that we as architects, as designers, as engineers have to solve. So let me explain that very simply. We have a problem, and we're going to give that problem to one computer, one CPU to solve. And the computer will need about 10,000 seconds to solve it, and it will cost about 16 cents. Well, with the power of the cloud, we can give that same problem to 10,000 computers at the same time, and they will solve it in 1 second at no additional cost. The ability to apply infinite number of resources at no additional cost to solve a problem is the first in human history. And it will forever change our lives, and it will definitely impact the way we make and design things. So how does that impact design? When computation was finite, we, the designers, decided, we, the users, directed the tool. We, the users, decided when to call simulation to validate our design. So, for example, if I design this car seat, what do? I explicitly design it in the software, and then I decide to make simulation to validate my design. And then I wait a couple of hours, sometimes 10 hours, to validate the design. The simulation comes back. I see in the red zone that it might crack, so I'm starting to change the design, add a little bit of material to pass the simulation. Did I make a better design with that? Maybe. But did I make an optimal design? No. Now, with infinite computing, what we will do, instead of evaluating one option at a time, we can evaluate many options at the same time. That is the value of the infinite computing. It can extrapolate, it can mutate, it can mash up thousands, infinite numbers of designs simultaneously. Welcome to generative design. Generative design takes goals that are set by a designer, by an engineer, such as cost, weight, style, material, etc. Basically, think of any criteria that describes the problem, and uses intelligent algorithms, very often based on evolutionary patterns, to basically create a massive number of design options, design variations. We say it opens the design space to evaluate all the options. So with generative design, instead of applying simulation after we finish design, or do simulation during design, we're going to simulate to design, to discover all the possible options within the entire space. And this evidently will lead to major reductions in cost, in development time, material consumption, and in product weight. But it's not only that. This new approach let us design in a new way and let us see options and variations and designs that we could never thought of before. Now, since you all love motorcycles in India, it seems, I wanted to show you a competitor to your motorcycle. These are the Lightning motorcycles. It's an Autodesk startup, and they have produced the fastest motorcycle in the world. I ride a Ducati. It's not as fast as this one. So, did I mention it's an electric bike? So winners stay winners only if they improve. So they keep on thinking, what can they improve to make this bike stay the fastest bike in the world? And one is to reduce the cost, the weight, to improve the lightness of the bike. So here we see a swing arm. That is usually a very strong part. It's quite heavy because it has lots of forces. So they started to look at how can they reduce the weight of this part. It's a complicated problem because it has a lot of various forces that come to it, and it has to hold the whole bike. So we applied we applied generative design to the problem, and we arrived to something like this. As you can see, generative design mimics nature. What you see on the first image is actually a cat pelvis. The second one is a dog pelvis. The third one is the design we arrived at. But that was when we gave generative design the shape to start with, and then we optimized the topology of the shape. But we don't have to start like that. Instead of using generative design just to converge from our design, it can diverge from our goals. In this case, we will just tell the goals. We will just set the constraints. Where are the forces? Where is the weight? And we will get the system generate many, many options. And then we, as designers, decide which of those options makes sense, understanding the trade-offs that we cannot calculate at the same time because there are many of them. And then we can apply simulation to validate the design to finally arrive to something like this. This is a very curious design, and it's not a design that somebody would have come up with. So there are very interesting things coming on. From last year, you might have remembered that we work a lot with Airbus, and they're really interested in improving the experience of flying, making flying more affordable for us, but also making it better for the world, making it more sustainable. So the first project we did with them was to address one of the partition walls that is very heavy, and to use generative design to basically reduce the weight of this partition wall, but without impacting its bare function, which is to hold the stewardess seat. So we ran it again through the algorithms, and as you can see, it was crunching and crunching through many variations, giving us feedback all the time. If you do this, you gain this, but you lose this. So finally, we arrived to a number of selected options, and from something that was completely solid, it ended up being something that was using 1/3 of the material. It was 45% lighter, and it saved Airbus a lot of money. Now listen to this. Airbus thinks that if they implement this partition wall on their entire fleet of A320s, that would basically be like removing 60,000 cars from the road. It's quite impressive. Now we work with them on a new project. This is about changing the seat frames. And again, if we make them lighter, that impacts the cost of fuel, that impacts the cost of the price for the ticket, and also it's better for the environment. If this project works out, they will be able to reduce 0.5 ton on the bigger planes, 200 tons of annual carbon emission, and they will be saving over $200 million per plane. That's quite amazing. This is not using technology just because it's cool or just because you can. It's real economic value and value for the planet. Now here is something interesting. Only when we printed the partition, we realized how difficult is it to understand it. We couldn't tell where will it fail, but a computer could. We humans could hold it in our hands, but we could not hold it in our heads. It's too complicated. Our designs, our structures that were once so easy to understand are becoming inscrutable, really difficult to understand. Now you may say, okay, generative design seems like something interesting for product design, but what about AEC? What about architecture? Architecture is so complex, there's so many factors, you cannot apply this method to it. Well, we took upon that challenge and we had a compelling event. Actually, our colleagues in the Toronto office were just going to move into a new building. The building was already built, but we wanted to see, can we use generative design to impact the quality of the workplace? So we started with interviews. We interviewed all our colleagues and asked them, so where do you want to sit? Do you want to sit next to the window? Do you want to sit next to the kitchen? Do you like to be quiet and people not to bother you? Do you like to be in a community, etc.? So basically anything, any factor that was making their life and thus work better. And then we defined the goals. What's very important is that you define measurable goals. And then the system evaluated the survey data against the set of hard constraints, and we had hard constraints because the building was already built, so we had to agree where is the corridor, where is the kitchen, etc. And then we let the system go. The power of automation. Now think about all of this. We as humans could not have ever, it doesn't matter how good an architect I am, and I cannot think at the same time of so many factors and so many people, and the constraints, and the trade-offs, but the computer can. And it can visualize it, and it can give me information that I could never had before to make the right decision. This system generated, evaluated, and evolved over 10,000 options. And it arrived to something that our colleagues are quite happy with. We will tell you next year how did it go, but the first 2 months seem to be working out. What's important here is we were not just pushing cubicles or Lego boxes to understand how to do this. Our relationship with the tools changed. Earlier, we were just directing them. What we do now is we create a relationship in which the tool understands us, understands our goals, and is serving as a collaborator to offer options to us. So remember, generative design is not just about surface or volume optimization or topology optimization. It can help augment our own creativity. Now, many structures and products that we can generate with generative design result in geometry so complex that no subtractive traditional type of manufacturing can produce. It is thanks to additive manufacturing that we can actually produce these things. So let's talk about additive, or as we popularly call it, 3D printing. So unlike subtractive methods of manufacturing, where you take a piece of material and you carve out until you arrive to the shape you want, discarding a lot of material, in additive, we just lay layer of material and use only as much material as we need. That is the first value of additive, only as much material as we need. But that's just the first one. The second one is that we say complexity comes for free. In a 3D printer does not care if you're printing a box or if you're printing something unbelievably complex, because it's left, right, up, left, right, up, left, right, up. So that's another thing. The next one is the number of materials with which you can 3D print. It used to be 20, then 70, now it's over 150 of existing materials, but the future in printing will be developing new materials, new performing materials that can leverage the process. Another one is a printer can print an entire mechanism in one go. So this mechanism was not created out of 20, 30 printed parts and then somebody assembles them. No, if it worked in Inventor or in Fusion with all the tolerances, it will work directly printed like that. So it prints entire assemblies at the same time. Think about what will this mean for assembly line in the future. We'll probably not have them. Another one is that 3D printers can print multiple materials at the same time, but not only multiple materials at the same time, they can literally print every single voxel in different material, color, transparency, and physical properties. This is huge, and guess what? We don't know how to design for that. Our CAD tools are not ready to leverage the full power of 3D printing. So if all of this is so important, what do we in Autodesk do about additive? Well, we're determined to be industry leader in design, in simulation, and automation for advanced materials and for manufacturing processes. We're developing a portfolio of products and expertise around different materials, advanced polymers, fiber composites, adaptive machining, in-process inspection, etc. We've built abilities in our products to create designs that are printable, but also products like NetFab that not only prepare design to be printable, it also can optimize the design during that process, and most importantly, it can simulate it before you print it, because this part, printed out of metal, costs a lot of money. You better simulate and see that it will work before you actually throw it into the printer. We're also experimenting with voxel-based technologies. Why? Because if a printer can literally print every pixel, every voxel in different material and density and color, then we need to learn how to design for that. So this is not only topology optimization as a shape optimization, but as a material distribution across the product, so that we can design products like this, or we can create materials with non-linear behavior, so that our designers, you, can create beautiful designs like this one from Sawako Kaijima with beautiful, beautiful details of this table. 3D printing today prints small, prints slow, and expensive. But we want it cheap, we want it fast, and we want it big so we can go in AC, right? So we do something about that as well. We have a project Ashe. It's an OEM software that any one of you can use and build machines. And what it does really is it makes the fabrication process parallelized across multiple tools. So in this case, you're seeing 5 print heads, and what our software, Conductor software, does, it instruments them so they're all dancing together and print one large part. What's really important to remember is that this system is flexible enough to not only accept additive tool heads, but also subtractive, because the future of manufacturing is not additive, it's not subtractive, it is both. It's both of the two worlds that we will need to arrive to a better future. So, in the future, we'll be able to apply the same principles on every level, from nanoscale to urban level. We'll be able to print DNA, to print organs, to print fractured bones, to print custom prosthetics, to print food, to print new performative materials, to create new type of fashion, to create cars. This is already the first car that is 3D printing. It's Strata from Local Motors. To print buildings on planet Mars or on planet Earth, like this building from the Wind Sun Group that is actually costing just $5,000, and then can print 10 a day. It's low-cost housing. But this is just becoming stronger, bigger, and better. And there is a lot to see in the upcoming years. Now, Pat mentioned the magic word sensors. We also live in an age of sensors. The sensors are becoming so ubiquitous, they're becoming smaller, they're becoming more powerful, they're becoming more affordable. So today, with the laser scanner, for example, it's easier than ever to digitize the analog world around us. And once we digitize it, we can convert it to point clouds of buildings, of spaces that can then help us actually start working in the space without having to always first redraw in AutoCAD or remake in BIM in order to even start the task. So this is how a scan looks like, without any post-processing. And with a smart software, we can register individual scans with single click, we can visualize the point cloud in many different forms, we can measure it, and most importantly, prepare it for our hero apps so that you can then use it as a start or for capturing context of a project, for capturing progress in construction site, or seeing the difference between as built and as designed. There is another process. It's even easier. It's called photogrammetry. Today we have the possibility with simple photos taken with your iPhone, take a bunch of photos around an object or from a space, to automatically convert them to a 3D model. It's fascinating. Could you have done this with Max or Maya? Of course you could, but you need expertise. You need a lot of time to do this. And this is just taking photos and the algorithms do the rest. So now put these cameras on a drone, and we have a whole new world of access from the air, where we can easier than ever capture entire sites, either for pre-planning in construction or for land takeoff, etc. So here, the drones today are becoming so easy that you can walk and they follow you like a dog. They can be flown easily by defining a flying path, etc. A lot coming here. But this is not only interesting for new buildings. We're talking about, for the first time, possibility to save our heritage. We're losing our heritage on a daily basis due to tsunamis, earthquakes, wars, terrorist attacks. And we have obligation towards our future generations to save it and to capture it, to make a blueprint of what we have today, and maybe use it for further restoration, etc. In India, the government of Rajasthan is the absolute leader in this area. They have realized the potential of this technology, and not only they're using it to capture the gorgeous palaces that they have in Jaipur and all around in Rajasthan, but also they are planning to use that for further planning of the cities and marching towards the smart city concept. The Smithsonian is the biggest collection of museums in the world, and they are using the same technologies to digitize their collection that is 154 million objects. And they stay in museums, you don't see them enough, maybe some of you will never make it there. Well, how about putting the museums online, where curators can tell the story about their objects in a 21st century way, but also teachers can teach with this tool that is now an online tool that displays all of these digitized objects and teach in a more experiential way, in a way that the kids of today would love to learn. So imagine you're a teacher who teaches about the mammoths, and you tell the kids, hey, open the Smithsonian model and tell me how tall is the leg of the mammoth, or let's make some art with this mammoth. Let's make a sticker for the t-shirt. New ways to educate. The latest project of the Smithsonian digitization was the Apollo 11. You can see it actually in the exhibition hall. So we digitized the heck out of this object because usually nobody goes inside, and it was going to be open from the plexiglass box for another exhibit. So we did photogrammetry, laser scanning, structural light scanning, everything possible to capture a record of the Apollo 11. Today, you can take the AR/VR set in the gallery and actually sit in the Apollo 11 as the astronauts did. Professor Saunders from Penn Design is using the same technology to teach. He's teaching Baroque architecture, and very similar to your traditional vernacular architecture, Baroque is very complex. But when I studied architecture, we learned from floor plans and sections. Well, you cannot really learn like this, because Baroque, in this case, is architecture that is a combination of painting, of sculpture, and of the architectural elements. So what he did, he went to Italy and captured with his students 14 of the most iconic Baroque objects, Baroque churches, and he created beautiful topology of these churches. Then they created a website on which you can all experience these churches with beautiful imagery. These are, by the way, the interiors of the churches. Imagine you fill a church with water and then you freeze it. This is what you're seeing. And you can also see this exhibit in our exhibit hall. The idea is that the students now for the first time can understand the whole complexity of the Baroque architecture, take a church and start reverse engineering the language behind Baroque architecture. So you see, same technology, a lot of different uses. But sensors are not only smart to capture geometry. Sensors can also capture pretty much anything. So a couple of years ago, when we first started to talk about Internet of Things, we decided to again take another experiment with our own buildings. This is another building in Toronto, where we decided to put sensors on just about anything that was measurable in the building. And the idea was really to empower the existing building to be smart, to be responsive, to be able to have a voice, to give us feedback, to be alive. And that's what we did. And then we needed a way to visualize the data. This is an interactive building performance visualizer called Project Dasher that we're working on at the moment. And it combines sensor technology with cloud-based analytic to bridge the gap between design and building operations. This live dashboard will tell us at all times what's going on in the building, so we can finally understand the cold and hot calls and really leverage this to understand, did we design the buildings good, and what can we do about the maintenance. Now, one cannot talk about the future without talking about robots. Robots are lovely, and robots are scary, but they're nothing new. Robots have been existing for quite a while. That's how manufacturing happens. And they're very, very powerful machines. They can do a lot of things that we cannot do. But they have one big weakness. They're very difficult to program. So if you look at this assembly line here, if you wanted to make a change, to reprogram all these robots will take a year and an expert. And this is a real bottleneck. This bottleneck is what prevents companies to be more adaptive about their products, to change them more often, let alone to do personalized products. And this is the same reason why other industries like architecture is slow in adopting robots, because they're simply too difficult to interact with. And there is another thing. Robots are not quite aware of what's going on around, so if I pass by, they might literally kill me because they don't know that I'm there, or if the conditions change, they don't know what to do because they're programmed to do just one thing from just this location to just that one thing. So how can we make these robots, these machines that could be so powerful, be easier to use and create a new language to talk to them? And that is what our research group in Autodesk is doing. We're trying to see, can we develop a language that is much more natural? And can we, instead of giving robots specific tasks, directions to do one thing, teach them the principles of what we're trying to do, and then let them do it? And that's exactly what we're doing. So this is one of the robots that we call, it's a she robot. Her name is Ashe. And Ashe is a normal robot, only that we don't keep her in a cage. So we like the idea to be able to tell a robot what we're trying to do and then leave the robot do it on her own. So we decided Ashe to become a 3D metal printer. So we gave Ashe eyes to see what she's doing, but we also trained her to understand what she does. Now she's printing a chair, but when she finds an error, there is a closed-loop system, and she says, wait, this is not how it's supposed to be, and goes back and self-corrects. And as it self-corrects, the system becomes smarter and smarter and better. This, by the way, is the chair that we designed with generative design that Ashe was able to do. And while we're adding more functionality to Ashe, we're also exploring opportunities to enter into Ashe's world, which is this virtual simulated environment, full-scale environment in which we can operate Ashe very differently. By moving our hands, we can operate her hands and understand constraints, etc., before we let her go. And in the case of the welding, well, it's also good because the sparkles of the welding are not going to come in my face. But we have an even cooler robot. This robot is called Bishop. And we introduced Bishop to the very disorderly world of Legos. And we wanted Bishop to learn and recognize and assemble Lego bricks. Now, Bishop came to understand that he has eyes to see and hand to grab, and started to do what we were trying to tell him to do, or what he was learning to do. But it was going slow. We wanted to speed him up. Well, how do you speed up a robot? Well, you either let the robot learn on its own for about 3 years, and you're watching yourself getting old, or you get hundreds of robots at the same time, and each one of them learns a little bit, and they collectively learn something. But we applied a third method. We created an artificial world for him to learn in. What I mean is, we replaced, the video is not running. It crashed. This is technology, by the way. They promised that they can reboot it in 30 seconds, but we realized that one of these videos is having trouble, so sorry about that. So, let's try again. So what we did is, instead of hiring 100 robots to do this to speed up the learning, we actually put Bishop in a simulated space where we replaced what Bishop sees in the real world with simulated images, and now Bishop was learning in a simulated environment. We decoupled the learning environment from the real world. And by decoupling the learning environment from the real world, we decoupled time. Now Bishop is going to train himself overnight and making thousands and thousands of options until he really learns. We built a machine with curiosity and then let it run. And no longer Bishop is going to be confused when I throw a bunch of additional Lego blocks, because he didn't learn a recipe on a fixed position with a fixed object. He learned what I'm trying to do. And now imagine replacing the Lego bricks with something else. That is how construction will look in the future. And now imagine also that when one robot learns, thanks to the cloud, thousands of robots have learned at the same time. What we just saw in the last couple of minutes was machines that learn. We didn't program them. We couldn't program them. That's too complicated. This is machine learning. This is artificial intelligence, and it's not a buzzword. It's happening with every second more and more powerful, and we will be able for the first time to address unbelievable problems that we have not found solutions until now. And by the way, not even machine learning is new. All of you have already used systems with machine learning. When you search something on Google and it auto-completes what you write, that's machine learning. When you watch a movie on Netflix and it offers additional movies that you might like, that's machine learning. Same with books. Same with translation of one language to another. And of course, how can we not talk about self-driving cars? That is the latest scream of technology. The self-driving car is a machine learnable robot. Imagine if you had to program it. How do you tell a car of all conditions, all weathers, all people who might pass by, a dog who passes by, all the accidents? We cannot code that, but we can train a system to learn on its own by not making it an if-then machine, but rather teaching it the concept of driving. Imagine what will this mean for design, for engineering, and for construction. And for construction, you don't need to imagine it. Actually, it's already happening. So as you know, construction is a high-risk, low-margin industry, and a lot of these risks are happening actually on site. And it's a normal thing for a construction site to have hundreds, sometimes 1,000 issues a day, which sounds like a nightmare, but don't stress, because for the first time, we're seeing the light at the end of the tunnel. Welcome to BIM 360 IQ. So, you know, we have BIM field, and we had 10 years of BIM field data gathered, and we gathered about 24 million documents. And with simple classification, we trained a system that can inform the superintendent of any predictive risks that are coming on site. This is like a personal assistant to the superintendent, who can now wake up in the morning and open his iPad and look at all the issues that are surfacing for him. So from 1,000 issues, this machine learning system will tell him, today you have 3 water issues and 5 other issues, and he knows what to prioritize and how to do that first. We started with BIM-IQ with classification method of just saying what's more urgent and what's less urgent from problems. But we're now moving towards computer vision, so we want to train a system that when a camera recognizes a darker patch around the window, then that must be water, that must be water leak, so it will again surface that. Or for example, that it recognizes that there is no guardrail on a scaffolding, that's a safety issue. We'll be able to alert the workers on time. And if a subcontractor has really had a bad reputation or bad projects behind him, don't you want to know before you hire him on a project? This dashboard will also inform you of the previous experiences with that subcontractor. So with machine learning, instead of looking at the back mirror in construction like we used to do until now, we look forwards. And not just forwards. We're able now to augment the data with GPS, augment the data with reality capture, and put the data of construction at the center of the process. And we can help construction industry in different ways as well. We can apply robots on jobs that are really, really dangerous. At the moment, we're doing this experiment in our lab, and this is a robot that will be able to place curtain walls on high rises from inside. And at the moment, we're training it with VR systems, so we are operating it. But after a certain number of operations, it has learned to do it on its own. If there is anything to remember from this, is that data is the new fuel, and machine learning is what converts data into insights. All of us tomorrow will be in the insights selling business. So to recap, if we stayed in the world of finite computing, your products would have remained in a box. Our software would have remained locked in a box. In that world of finite computing, our relationship with the tools would have stayed directive, rigid, would have been based on calculations, on recipes, on complicated algorithms to code. Now instead, imagine this world of infinite computing. In this world, we don't push software once a year. In this world, our softwares are connected. They're alive. They're never ending. They're never finished. And so are your products as well. Data is the fuel, and machine learning is what makes insight of the data. In this new world, our relationship with the tools will be adaptive, will be fluid, will be natural, and we'll be teaching the machines to reason rather than follow stupid recipes and be confused when those recipes go wrong. The most important thing is to understand the power of these tools and to be able to let go. Don't be scared for your professions, because like with every technological advancements, some jobs go away, but others are created. In this case, what you're getting is the brain, the global brain of the whole world, helping you on every task. You just get more data to be a better designer, to be a better engineer. So from intelligent software to intelligent assistants to trusted collaborators, our tools and us together are on the verge to solving for the first time the biggest problems in the world. Thank you.
Okay, really a nice job, Tatjana. Another round of applause, please.